In this video, we're looking at kinematics with integration. So we have done kinematics before with differentiation. Usually we would have a displacement function given to us in the question. You do the derivative to get velocity, and if you want acceleration, you do the derivative again. In the integrals topic, we usually have a velocity function, and we're going to be integrating it to answer questions about displacement. Or sometimes you might even start with acceleration and have to answer questions about the displacement or the velocity. But basically, if you're going to differentiate displacement to get velocity, the other way around is integrating. So that's what we'll be looking at. We'll do an example question. So here's the particle. It's got a velocity of 2 take 4t. We want to find velocity at these 3 times. So velocity at 0, velocity at 0.5, and the velocity at 1. So we'll look at what all these equal. Now you absolutely can work these out by hand. So 2 take 4 lots of 0 would give you 2. That would be the velocity at 0, subbing in t equals 0 there. 2. That's in meters per second because we got a velocity function. We can do the same thing for the rest, but it's probably easier if you graph it. 2 take 4x instead of t. Draw that. And then we've got trace. 0 would give us 2 for the y value. You can do trace at 0.5 would give us 0. And if we want the velocity at 1, we can go trace 1 gives us -2. So if you want to interpret this, it's moving right. This is turning around. And this is moving left. So that's how we interpret those 3. Okay, find the displacement of the particle after 2 seconds. So displacement, in general, is the integral from between 2 times, t1 and t2, of the velocity function. So after 2 seconds, so we're integrating from 0 to 2 of the velocity function. And if we've got that graphed, we can just do the integral. So I'm going to go Shift G solve. I'm going to go mixed because we'll see why later, we'll need it. And I'm going to go from 0 to 2. It does that integral there. And on your calculator, you can see that it spits out 2 numbers. We've got the integral there, which is -4. And that's the answer to this question. So this number here is the displacement from 0 to 2. Okay, so that's what we get. And we can say the displacement is 4 meters left of the starting point. I'm going to be very careful. Left of the starting point, not necessarily left of the origin, because we don't know where the particle starts. Okay, next we need to find the total distance. Now, let's think about why this integral itself is 4 and the difference between distance and displacement. So if I'm a person who walks right 5 meters and then turns around and walks left 2 meters, in this situation, the total distance is 7 meters and the displacement is 3 meters right of the starting point. So that's the difference between distance and displacement. Displacement is like the difference between where you started and where you end up. Distance was the total distance that you traveled. Let's see it in this example. So we've learned the displacement is -4, so we're 4 meters left of where we started. Spoilers, the distance is 5, so it's that other number there. But we can work it out as well. So this integral breaks into 2 pieces. So that there is the integral from 0 to that number's 0.5 of the velocity function. And we can work that out on the calculator. So if we go across to integral 0 to 0.5, so you get 0.5 for that little area there. And that is the integral from 0.5 to 2 of the velocity function. So that integral there, we can work it out. Shift G solve across to integral. There we go. 0.5 is the lower, 2 is the upper. Minus 4.5. So you can see why the displacement is 4 meters left, because in this situation, the particle moved 0.5 meters right, and then it turned around and it moved 4.5 meters left. So the total difference between there is 4 meters left. And the total distance you traveled was 5 meters, because you've gone 0.5 and another 4.5. So with the distance, in general, this is area contained by velocity graph. If you want to write out an integral expression for this, it is 0 to 0.5 of the velocity function. And the other integral is 0.5 to 2 of the velocity function. And because this comes out as a negative, this last bit, you put a minus there. It's 0.5, take minus 4.5, which is 5 meters. Now, I want to be really careful here. You can basically just jump straight from there to there. If you've got a velocity function, when we did G-solve integral and mixed, and we typed 0 to 2, the calculator does immediately tell you minus 4 is the displacement, and the area there, 5, is the distance. So you can get it pretty much immediately without doing this split up here. But it's important you know why it works. When does the particle turn around? It turns around when the velocity is 0. So we got the velocity function here. It was 2 take 4t. So 4t is 2, so t is 2 over 4, which is a half. So that's when it turns around. Cool. And you can think of it, whenever this graph was above the axis, we were moving to the right. There, we're like turning around, and then for the rest of the time, we're moving left. Now, last thing we need to do is find the displacement function. So in general, the displacement function is the integral of the velocity function. Now, you might think this is very similar to part B, but part B was the displacement between two times. This is just the displacement function in general. So the velocity function was 2 take 4t. We got 2t take 4t squared over 2 plus c is the integral. Don't forget plus c. And then that simplifies down to this. Now, that is s of t. And this thing here tells us that at t equals 0, well, s is 7. So that's what that bit's saying. That is 7. And all of our t values are 0 there. And we can use that to work out c. If you do this, you're going to get 7 is 0 plus c, or 7 is c. So the displacement function there is 2t take 2t squared plus 7. Cool. Now, one thing that I do want to point out is that if I work out s of 0, I'll get 7. And if I work out s of 2, you're going to get 2 lots of 2. Take 2 lots of 2 squared plus 7, which is 4 take 8 plus 7, which is 3. So that's s of 2. So at t equals 0, s is 7. And at t equals 2, s is 3. So I don't know what happened in between those 2 points, but what I do know is that the person moved 4 meters left during that time, because there were 7 meters right and then they ended up 3 meters right. That means they've moved 4 meters left in that time. And what do you know? That was the answer we got for part B. So that's how those two are related. And that's why I wanted to be really careful when we interpreted this. The displacement is only 4 meters left of the starting point. If we had started at 7, we end at 3. That is 4 meters left.